Okay, let's talk about the velocity and the duration of contractions. How fast and how long muscles contract is dependent on the muscle fiber type. Scientists have studied muscle fibers and they've divided them into several categories, whether they're slow fibers or fast fibers, and then whether they use oxygen to get their energy or they don't. So, oxidative would be aerobic pathways, glycolytic would be anaerobic pathways. So they've used these two features, whether they use oxygen or not, whether they're slow or fast, and put them into three categories: slow oxidative, fast glycolytic. If I'm a slow oxidative, that means that I'm going to have oxygen. So my myoglobin that holds on to oxygen is going to be high. I'm going to be using glycogen to glucose in the glycogen. I'm going to use glucose to break down, or oxygen to break down glucose into energy, so my glycogen stores are going to be low. Since I have to have a good blood supply to bring in new glucose because there's not a lot of glycogen stores there, I'm going to be very vascular, so I'm going to be red. What is the organelle in the cell that does cellular respiration or aerobic respiration? The mitochondria, so I'm going to have many, and I'm going to be a very small fiber. If I'm fast oxidative, I'm also going to have high myoglobin for the oxygen. I'm going to have a medium amount of glycogen. I'm going to have a medium amount of blood vessels, so my color is going to be pink. I'm going to have many mitochondria because that's where I do oxidative, and I'm going to be a medium size fiber. If I'm a fast glycolytic, I don't need the oxygen, so my myoglobin is going to be low. I'm going to need the glycogen to break it down into ATP fast, into glucose, into the ATP fast. I'm not going to need a good blood supply because I'm going to have what I need right there in the muscle, so I'm going to be white in appearance. I don't need the mitochondria as much, so there are going to be few of those, and I'm going to be very large in diameter. So my bigger muscle fibers are going to use fast glycolytic methods, where my small muscle fibers are going, and medium muscle fibers are going to use oxidative. What kind of actions do you see with slow oxidative? That would be those that you use during endurance activities like a marathon. Fast oxidative would be like walking or sprinting, and fast glycolytic would be short, intense things like hitting a baseball or jumping up. So scientists have put muscle fibers into categories based on what kind of ATP method they use and whether they're big or they're medium or they're large. And by knowing those two things, you also know how much glycogen, what color the muscle fiber is, and how many mitochondria they have. So that was skeletal muscle. Let's very quickly talk about smooth muscle. We'll talk about cardiac muscle in AMP2. Remember that smooth muscle is spindle shaped. Get that to work. Spindle shape, where it's going to be skinny on the end and fat in the middle. Fat in the middle and skinny on the end. That's what we mean by spindle shape, with one central nucleus. They're going to be about 2 to 10 micrometers and several hundred micrometers in length. Remember, that's very small compared to skeletal muscle. Skeletal muscle is 20 times wider and 1,000 times longer. We can't see micrometers, but we can see skeletal muscle. There are no mysiums associated with smooth muscle except for endomysium. It's organized in sheets of closely opposed fibers, and most of the time, like in the digestive system, you'll have one set of fibers running circular around the lumen and the other one running longitudinal, so that they can alternate in their contractions and give you what's called peristalsis. Now, instead of having a neuromuscular junction, what we have is viscosities at a diffuse junction. So that you have all of these viscosities branched out across the sheet, and it's going to release neurotransmitters that diffuse across, and so the whole sheet reacts at one time. These release neurotransmitters into a wide synaptic cleft to diffuse over a wide general area of the smooth muscle. There are no T-tubules. Instead, you're going to see that the smooth muscle has these little indentation called cavenolae or cavenolae. There are no striations, no sarcomeres, no troponin, but they do have actin and myosin, but instead of being arranged in alternating rows, they're arranged like stripes on a barber pole, so that we squeeze down or we make it wider. So here they're relaxed, and here they're turning and squeezing the smooth muscle like a corkscrew. Now, remember that calmodulin helped to keep the calcium away from phosphates in the muscle. In the skeletal muscle, in smooth muscle, calcium binds to calmodulin, which activates a myosin light chain kinase, which catalyzes ATP and causes the shortening. So that's how you get your ATP to cause the contraction of smooth muscles. Calmodulin is bound to calcium, and that activates an enzyme which catalyzes ATP. Now, the contraction in smooth muscle compared to skeletal muscle is slow, and it's sustained, and it's resistant to fatigue. It is 30 times longer. It can contract 30 times longer than a skeletal muscle. So it contracts over long periods of time, and it uses 1% less energy. Some of them have gap junctions between the cells so that the cells contract in units. Some of them have pacemaker cells so that it can send a contracting impulse at a certain pace. For example, in your stomach, you have pacemaker cells that send a peristaltic wave from the beginning of your stomach to the end of your stomach so many times a minute to mix your food. In your book, and I know you have an e-book, the old book, it was page 310 to 311, there is a table 9.3 that compares the three kinds of muscles, skeletal, cardiac, and smooth, and it shows you where it's located in the body, the basic shape of the cell, the connective tissues that support each kind, the presence of myofibrils, the presence or absence of T-tubules, the sarcoplasmic reticulum, whether it has gap junctions or not, whether it exhibits a neuromuscular junction or has some other type of junction between the nerve and the muscle, and the regulation of the contraction and the source of calcium. And the site that the calcium binds to, notice in the smooth muscle that it's going to bind to calmodulin that's going to activate the myosin head. Whether you have pacemaker cells, the effect of the nervous system, the speed of the contraction, and so on. And so this table shows you some major differences between the three kinds of muscles. On the test, I might say blah 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 blah. These are all characteristics of what kind of muscle. I wouldn't just give you one characteristic. I would give you several, but you should be able to compare and contrast the three kinds of muscles. Remember that this is breaking a muscle down into its fascicles, its fibers, and its myofibrils, and we have this division because of the epimysium, the perimysium, and the endomysium. This is a neuromuscular junction. Number 10 would be the axon terminal. Number 11 would be the motor end plate. Number 12 would be the calcium that's going to come in. 13 is the vesicle releasing its acetylcholine. And so you see on 14, acetylcholine is going across the cleft, and that's going to cause the sodium channels to open in the motor end plate. Sodium coming in is depolarization that causes the terminal cisterns of the sarcoplasmic reticulum to release calcium. It binds to the troponin, pulls the tropomyosin down, exposes the binding site. If the myosin is in a power, has been cocked, it's going to attach to the actin, and you're going to have a power stroke. Remember, these are T-tubules, so we can send this wave of excitement deep into the muscle cell. And that concludes Chapter 9.